So now I'll finally argue that the image of this function is an ordinal. To do so, I want to get the, so to speak, in some sense, the min of its complement. Intuitively, as we've discussed, that min of everything above it, basically, will determine an initial segment equal to it. We'll argue our way to that in due time, but at least to get us going, let's argue that the image of the function is this min, the min of all ordinals, which are not isomorphic to any initial segment. Now, we need to know that this min exists, in fact, because this is, after all, a subclass of the class of ordinals. We know that every subset of a particular ordinal has a minimum element, but we don't know that about the class of all ordinals, so that actually deserves a bit of proof. The proof goes quite a lot like a proof given not long ago, namely, we take any non-empty class of ordinals, and then we can pick any arbitrary element, call it alpha. If it is minimal, we're done. If it's not, then we know there is something less than it, call it beta, and that is also in C, right, by assumption. And then because it is less, therefore it is in alpha, and since it is in both alpha as well as C, then it's in the intersection. This should all look fairly familiar. I'll skip the rest of the proof because it is probably pretty obvious and familiar at this point. So, okay, we now know that this set has a min. Now we have to establish that the image of the function is equal to that min. We can easily show that this, the image of this function is an ordinal by showing that it's transitive and well ordered by inclusion. So that is fairly easy. And so I skip it. Now, I also want to show that if we have any other ordinal alpha, and we suppose that it is less than the image of the function, but also an element of, right, or an element satisfying this property, right? I'm going to attempt to produce a contradiction, right? So I am assuming that there is an alpha in this set which is less than this particular ordinal, f of w, and I will derive a contradiction, therefore showing that no such alpha really exists. Okay, so being less than the image of the f of w, the image, then it is therefore included in it. It is therefore isomorphic to some initial segment by definition of the function, right? For this step, you have to recall how we defined f, but by definition of f, it implies the existence of such a thing, contradicting the idea that it would be in this set. We have our contradiction, proof complete.